Record this. And we'll even put a date on it.
I'm here, team.
This is good. We've got a point, and the point we took was 103. 1, 0, and z would be 3. Okay, so this gave us that paraboloid coming downward. Let me attempt to draw this. This top right here is 0, 0, 4. Okay, that's what that is. We've got the point 1, 0, 3, and I'll say the point is right here. That's our point. Okay. Okay, we want to find the equation of the tangent plane to this surface at this point. We have the point 1, 0, 3. We need that normal vector. Where do we get it? We get the normal vector by doing the following. I'm going to let W, a fourth dimensional object, equal 4 minus x squared minus y squared minus z equals 0. Okay? What this does is makes our surface a level surface for this fourth dimensional object, this function of 3 variables. Okay? If I were to set that equal to 1, I would get another paraboloid. It would be another level surface. And if I were to change this to 2, I would get yet another level surface. Yes?
I mean, if you were to change it to 1 and 2, what kind of characteristics of the surface would change exactly?
Let's see. What it would be the fact that it would raise it or lower it. It seemed to me it wouldn't change much else. Because if you solve for z and this is equal to 1, you would get 3 minus x squared minus y squared. That would drop it down. And it would drop it down some more and keep on dropping it down. So that fourth dimensional object basically looks like a paraboloid here, and then another one here, another one here, another one here. That's what it would look like. Okay, but that's what it would be. That's what it would be. That's a good question. Okay, so the gradient to this fourth dimensional object, which is partial with respect to x, partial with respect to y, partial with respect to z, that gradient is going to be normal to its level surface in the same way that the gradient to a function of 2 variables is normal to its level curve. That's what we saw the other day. We did the ellipse, and we had those normals that were perpendicular to the ellipse. And the first day we did it with the circle. We had all those gradients perpendicular to that circle, all pointing outward. Okay? This would be normal to the level surface. That's exactly what we need to define the tangent plane. We need a normal vector. This will give it to us. What is this normal vector? Well, partial of w with respect to x is a negative 2x. With respect to y is a negative 2y. And with respect to z, it's a negative 1. Okay. At the point P, 103, we're going to substitute in, and we're going to get the normal vector that we're looking for our plane. It's going to be negative 2, 0, negative 1. Okay. Now, what I did on the other one is to take a negative 1 out. 2, 0, 1. Okay. 2, 0, 1. 2, 0, 1. Okay. And what I did on the other one, I took a second point so I could draw the arrow. What I did, call this P, and had a second point Q. And I found point Q by adding 2 to here, which is 3, 0 to 0 to get 0, and 4. What I did, I took the 2, 0, 1, added it to this point to get a point Q, so that vector PQ, okay, vector PQ, which is 2, 0, 4 minus 3, 1 is the normal vector that I'm looking for. I could have kept the negative in there. It would have pointed it this way, and that still would have been a normal vector. But what I wanted to do is have the vector pointing outward. So I changed it around and made it pointed outward. Yes, Dave?
Is there a difference between the lowercase n and the n we were doing yesterday? Yesterday? Did you use an uppercase n the last time?
No. They're both normal vectors, I believe. I know what you're talking about, too, because I did notice that in the Mathematica. No, it's still the normal vector. That thing we were doing yesterday was to find a unit normal vector, not the principal unit normal vector. A normal vector that pointed outward. And it's the same as this one. Okay? Same as this one. Good question. Okay, so I have my normal vector. I've got the point. You define the plane. How do you define a plane? Well, in general, given a normal vector, let's say A, B, C, and a point, let's say x sub naught, y sub naught, z sub naught. In general, the equation of the plane containing this point having this normal, the plane has this equation. A times x minus x sub naught plus b times y minus y sub naught plus c times z minus z sub naught equals 0. Now why? Why would that be the equation of that plane having this normal containing this point? And the reason is this. If we have a normal vector, we have a normal vector and a point. Say it's a point right here. Just wrote it. All right, if we have this normal vector and a point, what would the characteristics be of another point on this plane? What would the characteristics be of any point on this plane? You take any point at all, give it coordinates x, y, z. What must be true about that point to be on this plane? What must be true is that this vector that you draw from this point x, y, z to our given point x sub naught, y sub naught, z sub naught, that vector must be normal to this normal. Okay? Must be perpendicular to this normal. That's the only way a point's going to get on this plane is if we were to draw that vector to this point, it's got to be perpendicular to this normal. That's true for every point on this plane. Take any point you want, draw the vector to this point, that vector must be perpendicular to our normal vector. Well, if that's going to be the case, if we have some point x, y, z, okay, and we have our point x sub naught, y sub naught, z sub naught, let's find the vector. The vector through these 2 points, okay, let's call this P, this is Q. The vector through those 2 points is going to be x minus x sub naught, y minus y sub naught, z minus z sub naught. That will be the vector through those 2 points. And that vector's got to be perpendicular to our normal. And how do you know if 2 vectors are perpendicular to each other? If their dot product is perfect. So the dot product of these 2 vectors must be 0. So if we take n, a, b, c, it must be the case that n dot v must be 0. Well, here's n. Here's our vector v. That's got to equal 0. That's the only way a point's going to be on our plane. Okay? What is this dot product? It's a times x minus x sub naught plus b times y minus y sub naught plus c times z minus z sub naught, and that's equal to 0. And guess what? That's the equation of the plane. Okay? That's the equation of the plane. Okay? So, getting back to this, okay, I'll go to another page. What do we get? Well, we have our vector. Our normal vector, we said, was -1 times 2, 0, 1. It doesn't matter if we take the -1 inside or out. I'll use 2, 0, 1. Okay. We have our point. Our point P was 1, 0, 3. The equation of our tangent plane is going to be 2 times x minus 1 plus 0 times y minus 0 plus 1 times z minus 3 equals 0. That's what we just found out. That's what we just derived. That must be the equation of that plane. Now, let's multiply this thing out. You get 2x minus 2. You get 0 there. Plus z minus 3 equals 0. 2x plus z minus 5 equals 0. And then what I did in the Mathematica was solve for z. Z would be equal to negative 2x plus 5. And hopefully that's what I had for the equation of my plane. Or 2x plus z equals 5. Maybe I wrote it that way. I'm not sure how I did write it. But that's it. That's it. Yes?
So yesterday we were solving for the gradient in the 2 space.
Mm-hmm.
Now what we've done is we just solved for z, brought it over to the other side of the equation, and then raised that gradient up. So it's just like a better version of the gradient we were finding in 2 space almost.
Almost, except now we are adding a component. It's a gradient for a in 3 space instead of 2 space.
Right.
So we had that extra. Yeah, that's it. That's it. We gave it an upgrade. We added a different. We gave it another component. We added another dimension to it. Is what we did. Yes.
Where was the gradient in your picture, though? It's supposed to point towards the tangent.
The gradient in the picture is this vector right here.
Oh.
That's the gradient. Okay. Yeah, well, it could point this way or this way. I changed it around. I took the -1 out and had it pointed this way. You see, the gradient,
And that points in the direction of the tangent plane? Or
no, the gradient is normal to the tangent plane.
normal to it?
Normal to it. So you got a gradient, which is our normal to the plane. Okay, that's the key, is right there. That gradient to the 3-dimensional object, to the 4th-dimensional object, that gradient for that function of 3 variables is normal to its level surface. Its level surface is our surface. Okay? So its gradient, this vector, is perpendicular to our surface, our parabola. And that's what we need for our normal vector to define the tangent plane. Yes?
So you changed the sign with the common factor of the normal vector.
I took a -1 out.
So that means
It was pointing this way, and I had it pointing the opposite
for
way.
any multiple of it, you're going to have the same tangent plane.
That's correct. That's correct. Because any multiple of this is going to be in the same, either this direction or this direction, doesn't matter. It's still normal to that plane. Okay. Now, what I did in addition to that, I changed the starting point, x sub naught and y sub naught, and to manipulate them. So what that did is rotated the plane around the surface, depending on where it was starting. But in all those cases, in every case, here, let's do a specific case. Let's take the point 004, and let's define that one. Let's do that one. Because you can see that one. At 004, we're at the top of the paraboloid. If we're going to get a horizontal plane, that's what we should end up with. Let's do it. We just found the gradient to be -2x, -2y, -1. That was our gradient to w. When we subtracted the z, just like Liam said, subtract the z, set it equal to 0, and we found its gradient to be this. Now we're going to take the point 004. Okay. What's the gradient at 004? It's going to be 0, 0, -1. So here's what we have. We've got our paraboloid. Bless you.
It'll be a straight line down, right?
Yeah, exactly. Okay, this is 0, 0, 4. The gradient is 0, 0, negative 1. This way here. Well, what I'm going to do is take the negative 1 out, like I did before, and make it 0, 0, 1, and point it upward this way.
Why do you measure that from the apex and not the origin?
Because it's at this 0, 0, 4 where I want to have my plane be.
Okay.
Yeah, that's where I want the plane to be. You got this okay? I don't know if you can see that. How much? I changed it around so it's pointing out this way. I think it's easy to do or see when we got pointed out this way. Okay.
What's pointing out?
That gradient. The gradient 0, 0, negative 1, which is pointing downward this way. I took a negative 1 out just like I did before, so it's pointing upward this way. Okay? That gradient, okay, right there, is our normal vector to the tangent plane. Go ahead, Dylan.
Is that 0, 0, 0 right there?
That's 0, 0, 4. That's a 4 there.
Oh, okay.
Let's see, my diagram is not all that hot here. Let me see if I can. Let me see if I can do this better.
Because there's no z. Z as an equation is negative 1.
This point right here, point P, is 0, 0, 4. My gradient is my normal vector. That normal vector is 0, 0, 1. Okay? I've got all the ingredients I need to define the tangent plane. Okay, let's make sure we're okay.
And then 0, 0, 1 is the negative 1 is the vector.
You got it? Go ahead, Dylan.
Well, shouldn't it be like below that point then if it's 0, 0, 1?
No, it's because
Well, I can move it anywhere I want. Yeah, 0, 0, 1 from here is this.
So it'd be 0, 0, 5.
Yeah, but I want it
Yeah,
at
yeah,
this point, so I'm
yeah.
going to put it there. Yeah, I'm gonna-
ahead of the vector.
So
It's all right.
because you wanted the vector pointing up, and you did the same thing in the first case.
Yes, I did.
Is technically both answers correct then, because you're
Yes.
looking at?
Yes.
So on an exam, would you have the only one of those, or would you put the positive and the negative in?
I'd have one of them.
Okay.
Trying to think of exactly what I asked you. I don't know what I asked you exactly, but I would have only one of them for sure.
So if we had a question where we had to do work off of one of those, would it make sense to convert it to the?
I'll tell you what happens. If you use the other one, well, this one's easy to show. If I were to do this one, the first one, with the one pointing inward, what would you get? Here, just let me mention this. Let me go back to here. The tangent plane that we got back here when we did this one, okay, here it is here. Negative 2x plus 5, okay? We would get, okay, this is, we got 2x plus z minus 5 equals 0. What we would get if we use the other vector would be a negative 2x minus z plus 5 equals 0. That's what we would get. And guess what? When you multiply by negative 1, both sides you get this. The two are equivalent. One's the opposite of the other, but they're the same. Okay, they're the same thing. Because you multiply this by negative 1 both sides, you're going to get this. They're the same equation. Okay, that's what would happen now. So it really wouldn't be any different. Okay, so let's define our tangent plane. You ready? We've got our normal vector. We got a point. Here's the equation of the tangent plane. 0, right here. 0, x minus 0, plus 0, y minus 0, plus 1, z minus 4, equals 0. 0 here, you get z equals 4. And guess what? The equation of that tangent plane, okay, to that paraboloid at that point is z equals 4. Okay? Everybody all set on that? Let's suppose instead of using 0, 0, 1, we had used 0, 0, negative 1 as our normal vector, the one pointing downward.
Where are the...
Okay, go ahead.
Oh, never mind. No, I got it.
Okay. Let's suppose we use this one instead. Let's see what the equation would be. It would be 0 times x minus 0 plus 0 times y minus 0 plus a negative 1 times z minus 4 equals 0. So we get a negative z plus 4 equals 0. Well, that's a negative z, or opposite of z, equals negative 4. But guess what? Multiply by negative 1, both sides. And yet, z equals 4. You get the same thing. Okay, you get the same thing.
Wait, so multiplying by the negative 1 is just the
Both sides by negative 1, which doesn't change the equation at all, you get the same equation. It's just like I said with this one over here. What do you think?
For a tangent plane, should we expect to only have a z value and have zeros for the...
Nah, you can't expect that.
So that's just the way...
Who knows what's going to happen? Yeah. What I'll do tomorrow, I think, is maybe do a different one. Maybe, wait a minute, I know what I'm going to do. I'm going to make one up and you guys will do it.
You are a genius.
Wow. What a thought. Is everybody okay here? Questions?
I got it. I killed it.
Questions? Go ahead.
Didn't the magnitude represent anything of the normal vector?
Nothing. All we need to do is have some vector that's normal to the plane. It doesn't matter what the length is. The length does not matter. Thank goodness. No, all right. Go ahead.
Can you tell us an applicable use for this in engineering?
Oh, whoa. Kansas
Rocket
plane.
science?
Hold
Didn't we
on.
already go over this?
Plane, surface. I can think about it in architecture, engineering in general. I'm not sure I know right off the top of my head. But in architecture, I can think about it.
Yeah, it's an
What's that?
Also in architecture. It's useful in architecture.
If you want to know, if you had a rounded, say, corner to some of the new buildings have these rounded corners, and you wanted to put a plane tangent to that rounded corner at a certain angle, this is what you would do.
Maybe it's going to build. Maybe you're going to
Yeah.
build a machine and you want to use it.
I'm pretty sure.